In this lecture, we'll discuss conservation of energy and momentum for a system of charged particles interacting with the electromagnetic field. The strategy will be the following. First, we'll write the rate of change of energy or momentum of the charged particles using the Lorentz force. Then we'll express it in the form that contains charge and current densities for the particles. We'll use Maxwell's equations to replace those with the electric and magnetic field variables, and then we'll see what the result will give us in terms of the energy and momentum for the electromagnetic field. Let's have Maxwell's equations available for our reference, and let's start with energy conservation. The Lorentz force acting on a given particle, F sub A, is equal to the charge of that particle times E plus V cross B. So notice in this part we'll be working in SI units, and Maxwell's equations on the right are also written in SI units. So the rate of energy change of particle number A, dE by dt, is F sub A times V sub A. The magnetic field does no work because the corresponding piece of the Lorentz force is orthogonal to the velocity. So we can write this generally as QA VA times E. No part due to the magnetic field. Now the rate of change of the total energy of the particles is the sum over individual particles. So we can write it as sum over A QA VA times E. Now we know that the current density is defined as sum over particles QA VA delta of R minus RA. So dE by dt can be written as a volume integral of J dot E integrated over all space. So J dot E is the rate of energy change of the particles per volume. It looks like the Joule heat if we consider a conductor where the current is induced by the electric field. If we introduce the energy density for the particles as E given the volume integral of some U sub P, where P stands for the particles, so U sub P is the energy density of the particles, then we find that dup by dt, the rate of change of particle energy density, is simply J dot E. So now let's work with this J dot E and try to express it in terms of something that will represent the corresponding energy change of the energy density of the electromagnetic field. So we need to start with J dot E and substitute the current from Maxwell's equations. Then we'll find an expression that only contains the field variables. So here we have curl of H minus dd by dt dotted with E. Now I want to use a vector identity that goes as follows. The divergence of a cross product equals B dot curl A minus A dot curl B. Let me prove it for you using vector notation. So the left-hand side we write as D sub I epsilon ijk aj bk. Using the product rule for the derivative, we have epsilon ijk bk diaj plus epsilon ijk aj di bk. In the first term, we can do the cyclic permutation for the indices of the epsilon. And in the second term, we're going to have epsilon jk ki. So if we put this together, the first term looks like b dotted with whatever remains. That's epsilon kij diaj. That's just the curl of a. Now, in the second term, we have a similar expression with a and b interchanged, but in addition, here there's a sign change because ki goes in the wrong order. There's di bk, and here's epsilon j ki. So that gives us a minus sign, minus a dotted with curl b, and this is the expression that I have here. So that was the proof, and now I use it for a equal e and b equal h. What we need is this piece here, e dot curl h. So let's rearrange a little bit and substitute curl e from Maxwell's equations. So now I substitute this in this term, which gives us minus del e cross h minus e dd by dt minus h dB by dt. In a vacuum or in simple media, where d is proportional to e and b is proportional to h, the last two terms can be combined into the full time derivative. This will give us d by dt 1/2 e dot d plus h dot b. We can now interpret this equation in the following way. We can introduce the notation for this quantity as u sub f and interpret this as the energy density of the electromagnetic field. And the E cross H vector, let's call it S, it's called the Poynting vector, and we can interpret this as the vector showing the flux of the electromagnetic field energy. So putting this together, because the left-hand side, J dot E, we have denoted it as the rate of change of the energy of the particles, the density of the energy of the particles. Altogether, we have d by dt, u particles plus u field equals negative divergence of the Poynting vector. This expression is the differential version of the Poynting theorem. The integral version can be obtained by integrating over the whole volume, where we have particles and the fields. So then on the left-hand side, we'll have the total energy of the particles plus the total energy of the fields in some volume. And then the right-hand side, we have a negative volume integral of the divergence. We'll convert through the Gauss's theorem through the surface integral of the flux of the Poynting vector. So the left-hand side gives the total energy in the given volume, and the right-hand side is the influx of electromagnetic field energy into that volume. Notice that in the derivation, we implicitly assumed that the charged particles do not cross the surface enclosing that volume. So generally speaking, the right-hand side should also have the flux of the energy carried by the particles themselves. Notice that the general form of the Poynting theorem has the structure of the continuity equation. So we could rewrite this as du by dt plus the divergence of S equals 0. And if you compare it with the continuity equation for the electric charge, d rho by dt plus del J equals 0, where J is the current of charge. Here S is the current of energy, and the energy density sits in the corresponding time derivative. So overall, these two equations are quite similar. They express the conservation of different quantity. In one case, it's charge. In the other case, it's energy. Let's now deal with momentum conservation. So the rate of momentum change for particle A is just the Lorentz force F sub A. So if we wrote the rate of change of the total momentum of the particles, we would sum up over all particles Fa, where Fa is the Lorentz force Qa E plus Va cross B. Now we could go from sum over particles to integration over the volume, and then we'll find the expression with rho E, where rho is the charge density, plus J cross B. Now, as we did for the energy conservation, let's take the integrand here, rho E plus J cross B, and substitute the charge density and the current density from the Maxwell's equations. That way we'll again get something that depends only on the fields. So rho is del D, so here we have E dot del D plus, and J is curl H minus dd by dt, and that's crossed with B. Now let's do some rearrangements. In the last term, we have negative dd by dt cross B. First, let's swap the order. That will change the sign. And then I'll rewrite this as d by dt of B cross D, and we subtract the extra piece, dB by dt cross D, that we've introduced. And now introduce dB by dt from Maxwell's equations. So that is curl E. So the second term here becomes plus curl E crossed with D. Let's assume here that we're working with vacuum, so that this expression here is equal to negative epsilon naught mu naught times S, where the S is a Poynting vector that we introduced when we discussed the energy flux. So this piece will go directly into the equation above. And now we have two terms that look similarly. So we have one term that goes as negative B cross curl of H, and another term from the last line, which goes as negative D cross curl of E. So these terms are similar, so we can work with one of them and then represent the other in a similar way. So each of these terms is a double cross product. Now we need to be careful to remember that the del operator only acts on what sits to the right of it. So in this first expression, del only acts on H. So if we use the double cross product, there will be a term with negative del HB, and here del only acts on H. So I'll supply the del with a subscript H to emphasize that, otherwise we'll forget. And then the other term is B dot del H, where we don't need to supply any indices because H already sits to the right of del and there is nothing else there. So now the second term obviously looks similarly. So I have del E D plus D del E. So putting everything together, this expression here is equal to negative epsilon naught mu naught ds by dt plus E del D plus all the stuff that's written in blue. Let's now rearrange a little further. We'll take E del D and add it here. And then on top of this, we'll add to the term with magnetic fields, we'll add a term plus H del B. That looks the same way as E del D, but it's always 0 because del B is equal to 0 according to Maxwell's equations. So now we have these two similar lines, and we'll rework them in a similar way. So let's do the first one, and the second one will be similar. So first, let's rewrite this in tensor notation. So the first term goes as minus bj del I h j, where I use I as the free index. Second term goes as bj del j hi. And the last one is hi del j bj. The last two terms can be combined. This is a derivative of a product. We can write it as dj hi bj. We can also use the fact that we're working with fields in vacuum, so that B is equal to mu naught H. So in the first term here, we can substitute mu naught Hj for Bj, and then this whole term here can be written as negative 1/2 mu naught del I H squared. And then this whole expression can be written as a divergence of a second rank tensor. So we can write del J mu naught Hi Hj minus 1/2 delta Ij H squared. Now the other three terms with E and D fields will give a similar expression, and there we'll have del J epsilon naught Ei Ej minus 1/2 delta Ij E squared. So we can now combine them together, and then in our main expression write dj, and we can introduce a second rank tensor. Let's call it sigma ij, and sigma ij is the sum of these two terms under the divergence. So let's expose it. This tensor is called the Maxwell stress tensor. So now we can interpret the terms in this momentum balance expression in the following way. The left-hand side gives us the density of the Lorentz force. So that's the rate of change of the density of particle momentum at the given point, which is balanced by the negative time derivative of something else and the divergence of a second rank tensor. Notice that epsilon naught mu naught here is just the inverse of the square of the speed of light. So to interpret these results, let's introduce the notation for the density of the Lorentz force. So this expression here I'll write as the integral of some force density over the volume. That force density represents the rate of momentum imparted by the field to the particles. We can also introduce the notation G for 1 over c squared s. This is the quantity that sits here under the derivative. And then we can write the left-hand side is f. We'll take g to the left-hand side. So we'll have dg by dt. And the right-hand side is dj sigma ij. So the left-hand side may be written as the total rate of change of the momentum density of the particles and the field if we interpret g as the momentum density of the electromagnetic field. And the right-hand side shows the momentum flow for the field. Sigma ij has two indices, and one of these indices represents the direction of flow, and the other the component of what is flowing, that is the momentum of the field. So the expression here has, again, the structure that is similar to the continuity equation. The divergence of the momentum current is balanced by the rate of change of the momentum density. This is the differential form of momentum conservation, and the integral form can be found by integrating over the whole space. So the left-hand side will then be the rate of change of the momentum of the particles imparted to them by the Lorentz force, plus the total change of the momentum of the electromagnetic field. And the right-hand side is the surface integral of sigma ij dsj over the surface enclosing that volume, so that the change of the total momentum inside the volume is balanced by its flow across the surface. Let's now consider a simple example. So here's a screen that perfectly absorbs electromagnetic radiation. There's a plane wave falling normally onto that screen from the left, and we want to find the radiation pressure exerted on the screen. So the screen is perfectly absorbing, so there is no reflected wave. So what we can do is use this expression for momentum conservation. The force on the screen corresponds to the rate of change of its momentum. So let's pick a volume with a element of the surface that is parallel to the surface of the screen and right in front of it, and then use like a pillbox that extends into the screen far enough so that there's no electromagnetic field at the back end of it. So now if we integrate the expression for the momentum conservation, or rather use the integrated expression here, the left-hand side will give us the total force acting on the screen. So we can write total force. The rate of change of field momentum is 0 because the electric and magnetic fields retain their intensity, so we just need the right-hand side. Now in the right-hand side, we have an integral over the surface of the pillbox, but obviously in the geometry that we have here, the flux through the side walls and the back wall is 0. So the only flux is through the front surface. So the surface has a unit normal that points to the left. Let's call it n. And then the surface integral will give us the area of the front surface times sigma dotted with n. So sigma is the tensor, sigma ij. Now clearly the only component of the force that is not 0 is the component along n. So if we introduce the z-axis like this, the only component is fz, and here we're going to have sigma z, and n only has a z component, so it's just sigma zz, and n with this choice of the axis is simply -1, so we have minus a sigma zz. Now the pressure exerted on the screen is the force per area, so it's simply negative sigma zz. Now we need to find sigma zz from the definition. Now we recall that for a plane wave, the electric and magnetic field are normal to the direction of propagation. So we can, for example, pick the electric field like this and the magnetic field like that. And then sigma zz is obtained from here by specializing to I and j both equal to z. Now, the electric and magnetic fields are transverse. So with I and j both equal to z, this term and this term are both 0. So we find for sigma zz negative 1/2 epsilon naught E squared plus mu naught H squared, which just happens to be the energy density of the field with a minus sign. So here we have minus U, where U is the field density. Substituting this back into the pressure, two minuses give a plus. So we'll find that the pressure happens to be equal to the energy density of the incident wave. Let's recap what we've done about energy and momentum conservation so far. We considered first the rate of work being done by the electromagnetic field on the charged particles, and then the rate of momentum change, which is given by the Lorentz force density. And then we re-expressed the charge and current densities for the particles using Maxwell's equations through the electric and magnetic fields, and worked out the balance of energy and momentum in the system. Now, we know that in relativistic formulation, energy and momentum are not independent. Energy and momentum form parts of a 4-vector of energy and momentum, so we should expect that energy and momentum conservation should, in fact, form a global conservation condition that includes both energy and momentum as its different space-like and time-like components. So let's try to repeat the derivation in a fully covariant form. We'll be working in Gaussian units in this part. So first, let's recall the 4 current density. The covariant component looks like C rho and minus j. And let's try constructing the following vector. We'll call it F alpha with contravariant components, and we'll define it as 1 over C F alpha beta J beta. Here F alpha beta is the field strength tensor, and if we substitute the components of this tensor, which I'll leave it up to you to check, we'll find the 4-vector with the following components. The time-like component is E over C E dot J, and space-like component rho E plus 1 over C J cross B. Now, if we compare this with what we had before in the rate of work and rate of momentum change, you'll see that these are just these components. The difference here is because of the units. We used SI units here, and this is in Gaussian units, but this is the same thing. This is the density of the Lorentz force, and this is the rate of work done on the charged particles divided by C. So the structure of this is expected from the structure of the energy momentum tensor. Remember, that one looks like E over C and P for time-like and space-like components. So here the correspondence is exactly the same. So we could call this F alpha the 4-vector of the Lorentz force density. Particularly its space-like part is exactly that, the density of the Lorentz force. Now, if we start with this 4-vector, we should be able to substitute for J beta through Maxwell's equations and relate F alpha to the quantities characterizing the electromagnetic field. That should give us the balance of both energy and momentum at the same time. So let's see how this works. Maxwell's equations give us the expression of J beta in terms of the field strength tensor. That's minus C over 4 pi df beta gamma by dx gamma. Now, in the following, we'll use the simplified notation for the derivatives. So instead of d by dx gamma, we'll use d with the index corresponding to the transformational properties of the derivative. So if we differentiate with respect to the lower index of x here, d will carry the upper index gamma, f beta gamma. So now we can substitute J beta into this expression here and do some manipulations with it. So we have f alpha equals minus 1 over 4 pi, c has cancelled, and then I have f alpha beta d gamma f beta gamma. So notice that all the tensor indices match. We should always make sure that this matching is preserved. So gamma upstairs, gamma downstairs, beta upstairs, beta downstairs, and then alpha is a free index on both sides. Now let's rewrite this a little bit. We'll rewrite this as a full derivative of f alpha beta f beta gamma and subtract the extra piece that we've added. That would be f beta gamma d gamma f alpha beta. And now let's take this second term here and manipulate with it further. So we have f beta gamma d gamma f alpha beta. So first I'm going to use the antisymmetry of the tensor f, and I'll interchange the indices in both f's. So because I do two interchanges, each of them is giving a minus sign, overall there is no sign change. So here's gamma beta d gamma f beta alpha. So this comes from the antisymmetry. Now I use the fact that gamma and beta are both dummy indices, and I'm going to swap them. So this gives me beta gamma d beta f gamma alpha. And now, because here I have an identity, so this term, this expression is equal to this expression, I can add them together and divide by 2, and I'll get the same thing. So I write 1/2 f beta gamma, that's common to both of them, and then I have d gamma f alpha beta plus d beta f gamma alpha. Now we can use the other pair of Maxwell's equations. Remember, this here represents the second pair of Maxwell's equations, but there's another pair which in covariant form goes as d alpha f beta gamma, and then I have two other terms that come from cyclic permutation of indices, gamma alpha plus d gamma f alpha beta, and this is equal to 0. This is a combination of two homogeneous Maxwell's equations. So now we look into this bracket and we recognize two of these terms are from this equation. So we can substitute the remaining term with the minus sign, and we will obtain negative 1/2 f beta gamma d alpha f beta gamma. Okay. Now we notice that f beta gamma appears twice in this expression. First here and then here. So I can then rewrite this in an obvious way as minus 1/4 d alpha of f beta gamma f beta gamma. So now everything is written in terms of a full fourth derivative of some expression. So I can write f alpha equals d gamma, and there's an expression that I'm gonna denote t, and it has the lower index gamma and upper index alpha. And the tensor t goes as follows. There's minus 1 over 4 pi f alpha beta f beta gamma plus 1/4 the delta symbol alpha gamma f, let's call it mu nu f mu nu. I can now raise the index gamma and change it to beta, and I'll obtain t alpha beta minus 1 over 4 pi f alpha gamma f gamma beta plus 1/4. Here's a metric tensor g alpha beta f gamma delta f gamma delta. So this tensor is symmetric, as it's easy to check. And this is called the energy momentum tensor of the electromagnetic field. Energy momentum tensor. And because it came from the same derivation that we did before, when we derived the Poynting theorem and the momentum conservation from the density of the Lorentz force, the expression here should encapsulate both those conservation laws now in four-dimensional notation. So if we examine the components of the tensor T alpha beta, we're going to find our old friends, the energy density, the Poynting vector, and the Maxwell stress tensor. Specifically, we'll find that the time-like component of T alpha beta is 1 over 8 pi e squared plus b squared, which is the field energy density in Gaussian units. The three mixed components, T naught I, are given by 1 over 4 pi e cross b, which is 1 over c times the Poynting vector. And the space-like components, Tij, are given by the negative of the Maxwell stress tensor. So in matrix form, T alpha beta can be written as U, 1 over C S, 1 over C S, and negative sigma. And again, the energy and momentum conservation is given by this expression, which relates the four-dimensional Lorentz force density with the four divergence of this tensor with respect to one of its indices. In the absence of charges and currents, so if rho and j are all 0, that means f alpha is also 0. So we have the continuity equation for the energy and momentum of the electromagnetic field, and in components it can be written as du by dt plus del s equals 0, and the space-like components will give dg by dt minus del sigma equals 0, where g is the vector that we introduced before. That's 1 over c squared s. That gives the momentum density of the electromagnetic field. We have seen these equations before when we considered energy conservation and momentum conservation separately. If we set the particle energy and particle momentum to 0, you'll get these expressions. This concludes this lecture, where we discussed the basics of energy and momentum conservation for charged particles interacting with electromagnetic fields in vacuum.